Welcome to NASA's High Power Rocketry video series. In this video, we'll be discussing recovery. The rocket recovery system is vital because it returns all of your hard work to the ground to be flown again. And more importantly, it ensures the safety of you, fellow Rocketeers, and surrounding property. Developing a reliable recovery system is a challenging but important skill to master. The recovery system consists of a black powder charge that is ignited and pressurizes the airframe, where a parachute and recovery harness are housed. The pressurization separates the airframe and pushes the parachute and the recovery harness into the atmosphere. The parachute is sized for the weight of the rocket, the desired descent rate, and with proper packing will lower the rocket to a safe landing. There are two conventional high-power rocketry recovery methods, single deployment and dual deployment. Single deployment method deploys the parachute system in one single event and is also called apogee deployment or pop at the top. This involves using an ejection charge to deploy a parachute at apogee, or the highest point during the flight. The parachute then brings the rocket down for a safe landing. Apogee is the safest point for deploying the parachute because the rocket is traveling at the lowest airspeed. The apogee deployment event is usually controlled by an ejection charge built into the rocket motor. The single deploy method is what is commonly used in low-power rocketry. It is simple, but it has some drawbacks. First, if the apogee of the flight is high enough, or if the winds are strong enough, the rocket may drift off the launch field. Second, the timing of the ejection charge in the motor may not coincide with apogee. In this case, the rocket may be traveling too fast and the ejection event may damage the rocket due to the forces exerted by the parachute. A flyer can use an altimeter that senses the change in air pressure to determine apogee and initiate the black powder charge instead of using the motor ejection. This method avoids the challenge of guessing the correct engine delay. The second flight profile, called dual deployment, helps eliminate the problems associated with a single deployment flight. In a dual deployment flight, the rocket travels to apogee, where an electronic barometric pressure sensing altimeter deploys a drogue parachute. This small parachute is sized so the rocket will fall at a velocity high enough to prevent excessive drift. Then, at a much lower altitude, an electronic altimeter deploys a larger main parachute that slows the rocket down to a safe landing speed. Most high-power rocketry flights that use small motors or fly to low altitudes use single deployment. HPR flights with large motors that fly to high altitudes use dual deployment. For Level 1 HPR certification, you can use either method. Because dual deployment is crucial to safe rocket recovery, we will focus on this method. Dual deployment uses an electrical circuit housed in an isolated compartment within the rocket. The circuit consists of an altimeter to control the recovery events, a power source for the altimeter, a switch to open and close the circuit, and electrical matches to ignite the ejection charges. The ejection charges are generally made from a small amount of black powder, which when ignited, pressurize the airframe and push the parachute into the atmosphere to slow the vehicle down to a safe landing velocity. The altimeters generally have two outputs to fire an electric match. One is for the drogue parachute and the other is for the main parachute. The output for the drogue parachute is usually programmed to fire the electric match at apogee, or slowest velocity, but can be programmed to fire a few seconds after apogee. The output for the main parachute is usually programmed to fire the match between 300 and 1,000 feet, depending on the size of the rocket and the recovery area. To make parachute packing easier and more reliable, the main parachute and the drogue parachute are in separate compartments. As such, the rocket separates at two different sections, once when the drogue parachute is deployed and again when the main parachute is deployed. There are systems which house the parachutes in the same compartment, but those are less common. Information regarding those systems can be gained from an experienced rocketry mentor. Several steps can be taken to increase proper and reliable parachute deployment. First, flyers generally use a separate redundant electrical circuit to control the ejection events. Instead of using just one altimeter that controls an ejection charge for the drogue parachute and an ejection charge for the main parachute, the rocket uses a second altimeter to back up the first altimeter, which controls a dedicated set of ejection charges for the main and drogue parachute. Each altimeter needs its own switch and own power supply as well. In this configuration, there are two ejection charges for the drogue parachute and two ejection charges for the main parachute. This way, if an altimeter, switch, power supply, or ejection charge fails on one circuit, the separate circuit serves as a backup to ensure a good deployment. Another way to ensure good deployment is to offset the altitude at which the charges go off and to increase the size of the ejection charges in the altimeter circuit that fires the charges at the lower altitude. If the first charge for the apogee deployment event is programmed to deploy at apogee, the second apogee charge may be programmed to deploy 1 second past apogee. The altitude offsets are to ensure that the charges don't go off simultaneously, because this could overpressurize and damage the airframe. Essentially, the second charge serves as a backup. If the parachute gets stuck in the airframe, or if the first charge is undersized, the backup charge would further assist the parachute deployment. One of the most important actions for the proper deployment is to ground test the deployment system in its final flight configuration. The Rocketeer prepares the ejection charges, packs the parachutes, and assembles the airframe in the flight configuration. Then the ejection charges are ignited remotely via long electrical leads. Using long electrical leads and standing well away from the rocket helps ensure that you won't stand in the path of the ejecting parachute. It's important to ensure the parachutes successfully eject from the airframe. If the parachute gets stuck in the airframe, or if the deployment is weak, the Rocketeer should examine the size of the charge and check the method of parachute packing. It's better to find mistakes in the recovery system on the ground than in the air when safety is at stake. Plus, improper deployment could result in a lost or destroyed rocket. Assessing a properly sized ejection charge and ensuring a good ground test are skills that are taught by an experienced rocketry mentor. Let's briefly discuss how to size an ejection charge and parachute. The sizing of an ejection charge is based on the ideal gas law. The ideal gas law relates pressure, volume, and temperature of a system. Mathematically, the ideal gas law states that pressure, or P, multiplied by volume, or V, is proportional to the mass, or M, multiplied by the temperature, or T, and a gas constant, or R. Or PV equals MRT. R is the gas constant for burning black powder, and T is the combustion temperature of the black powder. Essentially, the combustion of the black powder will raise the pressure inside the airframe, and this will create a force which will push the parachute out of the airframe. In addition to the ideal gas law equation, we need a few parameters from our rocket: the diameter of the parachute compartment, the cross-sectional area of the parachute compartment, the length of the parachute compartment, and the force needed to eject the parachute. The amount of force necessary to deploy the parachute is dependent on the design of the rocket, the size of the parachute, and how it's packed, and how the airframe is held together. The necessary ejection force for your rocket will need to be determined with the help of your mentor. As an example, we have a rocket that is 4 inches in diameter with a 36-inch long parachute bay. We've assumed that we need 200 pounds of force to eject the parachutes. We solve for the mass of black powder by rearranging the ideal gas law to solve for M, where M equals the pressure multiplied by the volume divided by the gas constant multiplied by the temperature. Next, calculate the cross-sectional area of the parachute compartment. This is calculated with the formula for the area of a circle. A equals pi divided by 4 multiplied by the diameter squared. This gives a cross-sectional area of 12.56 square inches. Pressure is a measure of force per unit area, so we can substitute F divided by A for P in the ideal gas law equation to obtain M equals force multiplied by the volume divided by the cross-sectional area multiplied by the gas constant multiplied by the temperature. The volume is found by multiplying the cross-sectional area by the length of the airframe. Substituting the values into the rearranged ideal gas law equation gives a black powder mass of M equals 0.0082 pounds. The amount of black powder used in an ejection charge is generally expressed in grams, so using the conversion factor of 1 pound equals 454 grams gives M equals 3.72 grams. It's important to understand this calculation is only a starting point for the ground testing of an ejection system. During the ground test, you may find you may need more or less black powder, but you should never fly a dual deployment rocket that has not been ground tested first. Always test what you fly and fly exactly what you've tested. Now let's talk about the parachute sizing for a rocket. To pick a proper parachute, you need to know 2 things: rocket mass and desired descending speed while under the parachute. With a drogue parachute, the rocket should descend quickly enough that it doesn't drift excessively, but not so fast that the forces of the main parachute opening will damage the rocket. Under the main parachute, the rocket should descend slowly to prevent damage as the rocket touches down. A common descent rate for drogue parachutes is 70 to 100 feet per second, and common descent rates for the main parachute is 17 to 22 feet per second. The governing equation for this exercise is the drag force equation. The drag force equals 1/2 of the density multiplied by the velocity squared, multiplied by the coefficient of drag, multiplied by the reference area. Since we are sizing the chute for a specific descent rate at a constant speed or terminal velocity, it's important to realize that under this steady state condition, the force of the drag equals the force of gravity. Or more simply, the drag on the chute is equal to the weight of the rocket. Since the force of gravity equals mass times acceleration due to gravity, we substitute mg for Fg in the drag equation. As a result, mg equals 1/2 times the density of the air at that altitude, multiplied by the square of your target descent velocity, multiplied by the chute's coefficient of drag, multiplied by the chute's reference area. We rearrange the equation to solve for our area A. The most commonly used parameter for parachute sizes in the hobby is the diameter. So once we have found the area, we can find the diameter by using the equation d equals the square root of 4 times the area divided by pi. Let's pretend that we're designing a drogue parachute for a 10-pound rocket, and we want the terminal velocity under this drogue parachute to be 85 feet per second. Note that the density of air is 0.075 pounds mass per cubic foot, and the acceleration due to gravity is 32.2 feet per second squared. The exact coefficient of drag for a parachute varies by design, but a common coefficient is 1.5, which we'll use in this example. After rearranging the force equation as discussed and substituting all variables, we solve for an area of 0.79 square feet. As we said earlier, it's more common to refer to rocketry parachutes in terms of the diameter, so using our equation for diameter and substituting our variables, we obtain a diameter of 1 foot or 12 inches. Inches are the common unit of measurement for parachutes. To finish our example, for a 10-pound rocket, a 12-inch diameter drogue parachute will bring our rocket down at a descent rate of 85 feet per second. Chute manufacturers will calculate their reference areas differently, so it's important to ask how they calculated this value. This video provides basic insight on high-power rocketry recovery, but it's vital that you seek the guidance of an experienced rocketry mentor to learn the aspects of designing and testing the recovery system. This video is only a supplement to the guidance of a mentor, not a replacement. The most important aspect of recovery is to always test what you fly and fly only what you've tested successfully. One of the most exciting things you will get to do in high-power rocketry is testing ejection charges. Calculating your ejection charge is a great way to teach the ideal gas law. You can use the model we demonstrated earlier to calculate the ejection charge of your rocket, using your data and measurements. A few things to remember as you work through the calculations are that the ideal gas law as it deals with rocketry is PV equals MRT, where P is the desired pressure, V is the internal volume of your parachute compartment, and M is the mass of the black powder in pounds. Additionally, the temperature of the burning black powder, T and R, the gas constant, do not change. It's extremely important to remember that you are calculating the black powder amount in pounds, and it must be correctly converted to grams. This will give your students extra practice converting units, but all calculations should be double and even triple checked before testing. The descent rate calculation that we demonstrated is also an excellent classroom activity. Predicting a descent time and then comparing it to actual flight data can be very rewarding and fun for the students. A related activity which will also aid in recovering your rocket is calculating the drift of the rocket. Predicting the flight of your rocket can be fun, and testing it can be a whole lot of fun. Please remember to follow all safety practices in the NAR Rocket Safety Code, as well as the motto, test what you fly and fly only what you've tested. Thanks for watching the NASA High Power Rocketry video series, and good luck in all your rocketry endeavors.